Welcome everybody. I am Suchit Sharma and I welcome you to my YouTube channel group study group. First and foremost, do subscribe. And I am making this video on a priority basis and on immediate demand. So I would be trying to cover all the contents as deeply as possible. However, it is suggested that you do some hard work from your side too. Let's start. Why is this pen not working? Let's see. Let's open the file. Is that the case or will it not be working? I don't know. There seems to be some problem here. Let me open this. You know, I guess I will find it in downloads. Show in folder. No, 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 no. I don't think it is here. I think it is in documents. Not even in documents. Let's go to OneDrive. Mm-hmm. It's a file, I guess. Something files, I guess. Home. Not here, not here, not here. Why is this not working? Will I have to do this every time I start this? Not now, not now. I have downloaded this several times, so no, I want to try it for free. Finish. Where is it? Where is it? Yes, better. Okay, this is some PDF stuff. Okay, I don't believe in your Black Friday sales. Let me just check whether I'm audible or not. You know, Black Friday sales. Let me check the quality. The quality goes okay. It is pretty good. So let's start. Okay, let's start. What is this one? This is for D.B.M.S, right? D.B.M.S week 5, and this is the last, right? The final activity questions and the rest. Mm-hmm. This is for PDSA, right? So let's not go to. I don't think I would need this currently. This is for that. Good. Let's go to database, and in database let's start. You know, week. No, not week or anything. I need. lecture slides in PPT. So finally, what we would be learning is the last lecture by by Professor Partha Pritam Das. So we basically already know what is lossless joint decomposition. I don't think I need to tell you again what it is. So for a basic reminder, for just the people who don't know, lossless join is when we take a relation, divide it into two, perform a natural join on the divided two sub relations, and we again get the relation R back. Okay, from this we are getting relation R back. That is what lossless join decomposition is. So how would we, just by looking at the relation, how would we tell whether it is lossless or not? We would check these three properties, whether both of them will united present the whole relation, whether both of them have they must have at least something in their intersection, and their intersection should be dependency on either one of them, have functional dependency on either one of them. So let's say R1 and R2 when intersected should either have functional dependency on either R1 or either R2. These are the three, you know, three counts. Let's call it counts. Three counts. Okay, these are the three counts that you need to check. Let's move forward. This is an example that we are looking at. There are the boundary is not particularly clear. This is a whole table which was decomposed in the following two tables. Okay, let me just darken this a bit so that it's clear what we are talking about. And after doing this, after decomposing it into two different relations, uh, my mistake here. After decomposing it into two different relations, what we do is we perform a natural join on both of these, and what we get is this table. Now see, lossless join decomposition by name, what most of the people would think is, oh, some data must have been lost, or we would have made some mistake with the data, or there has to be some loss of tuples. But that is not always the case. In this actual case, we are actually gaining some data. We are gaining some additional data through natural join. However, we are not getting the original table itself, original relation itself, meaning that we have lost the original table. And hence, this is why we call it a lossy join. The join is lossy because while you performed, natural join on these two, we got two different. Let me take take a similar color. We got two different data, two different tuples, which never existed on the original table. In the original table, do you find Nick NY 2010? No, Nick NY 2010 doesn't exist. Steve Boston 301? No, Steve Boston 301 doesn't exist. So these are the two datas, these are the two tuples that got added and are useless and make the table lossy. Let's move forward. Let's check Okay, so let me also tell you how did they divide it. Okay, how did they divide it? They divided the data based on. Mhm. Is my pen available? Okay, yes. Say, so they took the following attributes, and the decomposed attributes are as follows. You know, supplier ID, supplier name, city of the supplier, and quantity. And this is part ID and quantity, as you can see. However, while performing natural join, the common between the two is used, right? So quantity is used between the two, which is not a super key and not a good choice for doing natural join. Hence, the common element between the two tables R1 and R2, let's call this R1, let's call this R2, and let's call this R naught, right? Let's call this R naught. So quantity is not a good good attribute to choose as a common attribute between the two, as quantity is not a super key. It is written quantity attribute is not a super key in supplier or in parts. And through the previous lectures we have seen how to find or how to justify or how to tell whether a given attribute is a super key or not. You can watch those lectures to pretty quickly and understand what I'm saying. Let's move down. Now these these semi tables or these decompositions or the composition that's provided here is perfect, as R1 and R2 when naturally joined, R1 and R2 when naturally joined, return the original table R naught. Return the original table R naught. Okay, you can see this decomposition, and from decomposition to you know return of the data. This is a lossless join. So how did we get this lossless join? We kept in mind the super key. We kept in mind super key. Let me show you. Now supplier ID is present in both the subtables, namely suppliers and parts, and common attribute supplier is a super key. Is a super key. So it is important to know that while decomposing a data, the common attribute between the two tables should be a super key. Okay, that was quick. Let's move forward. This is an example. You know, a theoretical example. Let's write. Let's not write. Let's check. Okay, so this is given relation, and this are the given functional dependencies. It can be decomposed in two different ways. Professor says that these can be decomposed in two different ways. One is R1 containing A and B, and the other R2 containing B and C. So lossless joint decomposition would be the common attribute between the two B, and and this B has the following functional dependencies. Okay, basically B can form the following functional dependencies using the already given functional dependencies. Okay, we already know that these exist, and while checking these, let's say we have two tables A and B. What we in reality are checking is all the possible functional dependencies that exist. So in R1, okay, let me mark this as R1 and R2. Okay, in R1, this the two functional dependencies that may exist is, one is this. See, I am not writing a arrow B and a arrow A differently, separately. I am writing this as a, a single unit. By now you must understand what I am writing. This is a trivial case. A arrow A is a trivial case, and it does not matter that you write it or not, but it is important that you write it in the D.B.M.S course of IIT Madras, because they are using it again and again. Or else I would have just simply written A arrow B, but they, as you can see, they are using it again and again, so I have to use it. And the other functional dependencies that may exist is B arrow BA. Okay, and over here B, again B arrow BC may exist, B arrow BC may exist, and C arrow CB may exist. Okay, C arrow CB may exist. What we are actually looking is whether the functional dependencies given in the question are satisfied or not by the union of both. Okay, by the union of both. Let me make this as a table. Okay, three levels. This is the table. This is the attributes, and later on we have marked the functional dependencies. This is table name. This is attributes, and these are the functional dependencies that exist. So the union between the two must cover all the functional dependencies in F. That is the question. So is A arrow B satisfied anywhere here or not? Yes, it is. It is satisfied here. Is B arrow C satisfied here or not? Yes, B arrow C is satisfied here. So the functional dependency that exists in F also exists in the union of R1 and R2. Hence, this is a dependency preserving table and a lossless joint decomposition. However, that is not the case when we how is that? However, that is not the case when we look at another example, being R1 being AB and R2 being AC. So let me all we need to change is a simple a bit of simple stuff. Let me remove this. Okay, so one being AC and the other being AB. A to C will exist, A to AC will exist, and C to CA will exist. C to CA will exist. Okay, I'm talking about the second part, right? The second way that we are decomposing the table. I have completed this much, and this is correct. So let me put across so that you do not get confused of as of what I am saying, right? And over here, now it is quite simple to understand. It is quite easy to see that the functional dependency AROB is satisfied in the second example, but not BROC. You can in no way find BROC, or in no way can reach BROC in either of them, right? And you should not go, oh, I can reach A from here, and then from the A that I reached here I could reach C. That is not the case. We should see individually whenever comparing the functional dependencies. It should be done individually. This is separate, this one is separate, and this one is separate. Okay, so the functional dependencies that are common are the union of both. Until and unless you do union of both, you won't be reaching. A here is different from A here. Okay, I think you understood. Let's move forward. These are some practice problems. Do them. Do practice them. Dependency preservation. So before I start dependency preservation, let me take a little break of water. Okay. Okay, so I'm back. Let's do this. Let's do this. Where were we? Where were we? Okay, we are audible and both. Okay, we are audible and visible both. Let's start. Okay. What just happened? Uh, what did just happen? Okay, so I somehow lost. You know that, but that won't be a big problem for us. Let's do this. We are 22 minutes in. I would really appreciate if I could complete it in a 35-minute video. And then what's left would be just activity questions. Okay, let's do this. Activity 5.5. Okay, lecture 5.5. Let's expand the slide. Let's expand the slide. Let's move forward, move forward, move forward. Okay, we saw this, we saw this, we saw this. बच्चों का नुकसान नहीं होना चाहिए. Let's go, let's go. Dependency preservation, right? Dependency preservation. Now, what is dependency preservation? As I just told you, the union between the two dependencies individually should result in the closure set of F plus of F. Okay, the closure set of F. So this is what we are looking for. The union of individual dependencies in all of the sub relations formed during decomposition should be equal to F original. So what are they telling you is R would be given, functional dependencies would be given, then is the join or the decomposition uh, preserving dependency. See, as they have given, is the decomposition preserving dependency or not, decomposition not preserving dependency. This is not possible, so this is we should not even look at this case, right? So what they would do is they would divide R into several smaller ones, namely, let's say R1, R2, R3, and so on. Okay, this is what they would do. All right, and then ask you whether these this decomposition of R decomposition of R into the following R1, R2 till Rn, is it dependency preserving or not? Is it dependency preserving or not? So how will you find? You will check functional dependencies individually in all of them, namely R1, R2, R3 till Rn, till you reach the last table that was formed. Once you reach there, you find all the individual functional dependencies. You would provide firstly a union over them, and then the closure set. Okay, you unite them and then perform closure set. If it is equal to the functional dependency that was originally given, then it is dependency preserving. If not, then it is not. It would be better if I if it would be really better if you see it once rather than just listening to it and imagining it. They have provided us with the examples below. Let's check. Okay, they have provided us with quite a good example. Let's see. So what they are giving us is a relation with the following attributes and a set with the following functional dependencies. Okay, now they decompose R into R1 having ABCD, R2 having BF, and R3 having D. R3 having D. Let me put it a bit smaller one. Okay, good. So let's check, is this decomposition dependency preserving or not? Okay, are all the dependencies provided in F, are they preserved or not? We need to check. Okay, so let's check for R1. Let's check for R1. All right, What they would do is they would list out all the possible functional dependencies that are available that you can make. So let's say if you took you took B, you took C, and you took D, right? So immediately what you did was you listed out all the individual functional dependencies that may be present, that may occur. Okay. Then you took a pair of two, A, B, B, C. Let me take another color. Then you took a pair of two, A, B, B, C, C, D, right? A, B, B, C, C, D, and listed out all the possible functional dependencies that you can make. All right. Then you took a pair of three, A, B, C. Let me remove this so it is better to read. Right. This is better. So now you took pair of three, right? A B C B C D C D A D A B and all. So that is what you did: A B C A B D A C D and B C D. So once you did that, the all the unique functional dependencies were, one of them would be this A B C D stuff, right? That it maps all of them. Okay. However, what you are looking for is this: are the dependencies satisfied or not? Are the dependencies in F satisfied or not? Let's not go there. Let's not go there before we do it for R, R2 and R3. What we did the same stuff for R2 and R3. We did the same stuff for R2 and R3. We listed out all the possible functional dependencies that we could make or we could think of. Okay, that this is the table and these are the functional dependencies that might exist. Okay, we are not checking that they exist or not. We are just checking that they might exist. And once we did that, we took a union between all the functional dependencies. We took a union between all the functional dependencies as here. And once we did that, we got a, let's say, functional dependency f dash, as they have used it here. We got a functional dependency f dash. What we need to check is whether f dash, whether f dash, the closure set of f dash, does it contain the closure set of initial f, right? Does f dash plus contain all the elements present in f plus, or this one, right? F dash and f individually is different. So we check is a to d present or not, right? A to d, is it present or not? Is it present? Yes, it is present. Now a to b, let me do it. Let's please do not do this. Just listen to me, okay? Don't read this one by on your own. It would be better if I do this for you. What you are looking for is checking uh, the functional dependencies present in F in all of them. So I took A. What this one suggests is A arrow B, A arrow C, and A arrow D. Does it exist anywhere in the R1, R2, or R3? Yes, it does. Right over here. Okay. Now, does A arrow EF exists anywhere? A arrow EF, A arrow EF, A to B to D. Okay. Now A to D to E. You know what? You could reach A to E once you made the F dash set, because in that you would have A B C D E, and then you would have D and E. Also, you would have B and F. Okay. So through here, through C, or sorry, through B, let me remove this once and for all. Okay, let me start this once again. It's pretty confusing for me itself. I don't know how you would have been understanding it at all. So let me do this. Let's restart. Okay, let's restart. Forget the part that I told you anything. Okay, you are provided with the following relation and the following functional dependency. You divided the relation R into the following sub dependencies. Sorry, sub relations R1, R2, and R3. You decomposed it into these three. You made and or you just figured out that, oh, these are the following functional dependencies that might exist in the following relations f1, f2, and f3. Now what you did was you united all of them. That is, this big thing is just let me, okay, it takes a bit of time. So this huge thing is just a single set. Remove all the boundaries. This is just a single set. Okay, once you did that, this is what you once you did that, you called this f dash. Okay, once you did that, you called it f dash. All right, once you started calling it f dash, what you now want to see is whether f dash plus f dash plus contains, you know, does it contain this f plus, let me remove this, it is too close, you would get confused. Does it contain f plus or not? Or does it, is it an exhaustive set over f, f plus or not? That's what you are looking for. Simple steps. First step, made the dependencies and write, made the dependencies for each and every relation, each and every table. Once you wrote the dependencies for all the tables, you performed union function and formed f dash. Once you formed f dash, now you will check all the dependencies in f dash plus. Okay, all the dependencies in f dash plus. So is a arrow b, a arrow c, a arrow d, you will be finding it in the whole set. Okay, let's start. Does a arrow b, a arrow c, and a arrow d exist anywhere, or is there a way to reach it? Okay, so immediately we can see that, oh, it exists by itself in the first relation itself. All right, does a arrow ef exist or not? So a arrow ef would exist, a arrow e and a arrow f would exist, because from this relation, using b, you would be reaching f, and from this relation itself, using d, you would be reaching e. Okay, so hence two are correct. Let's move forward and check whether BC arrow AD is true or not. BC arrow AD, is it true or not? So let's find BC somewhere. Is BC available somewhere? Yes, BC is available, and it directly corresponds to C and D individually. So this is true. Does BC reach to E? Yes, BC does reach to E, because BC arrow D exists. It will reach again to E through here. Does BC arrow F exist? Yes, through B itself it will reach here. Okay, so even two more are correct. Does B arrow F exist? Yes, B arrow F exists over here itself. So even this is true. And D arrow E exists here. So even this is true. Hence, all of the functional dependencies present in F are covered in F dash that we formed. Okay. So this means that all the dependencies are preserved. Let me tell you again, we wrote down all the dependencies that may exist for each of the table. We united them in F plus, F dash. Once we did that, we checked whether all the dependencies in F do they exist in F dash or not. Okay, does F plus equals to F dash plus or not? If it does, dependencies are preserved. If not, dependencies are not preserved. It's that simple. Let's do another example. Let me check. Okay, this is a testing algorithm. This is an example. This is another example. This is an example again. Okay, so let me do just that one example, and you can read the rest of them by yourself, because it is the same thing again and again. Okay, so let me do this fourth one. We are provided with a relation ABCD with the following functional dependencies. We divide it into the following three tables: A, B, B, C, C, D. Now from that we generate all the possible functional dependencies that we think they might exist individually. Finally, we unite these three. We perform let me do this. We perform union function, and thus we find F dash. And one by one we start checking for all the dependencies from F, right? So A arrow B exists. Yes, it exists. B arrow C, does it exist? Yes, B arrow C exists. Does C arrow D exist? Yes, C arrow D does exist. Okay. Does D arrow A exist? D arrow A, does it exist or not? So this is quite a long path. So D arrow C exists. From here we reach C arrow B. Okay, from here we reach here, and from there we reach here. B arrow A exists, right? So finally, this means that even D arrow A exists in the set F and in set F dash both. Hence, all the dependencies are preserved. Let's move on to the questions. This would be good enough, large enough, right? For the decompositions R, R1, R2, select all the compulsory conditions that must hold for the decomposition to be lossless. Okay, so union should be equal to R. Okay, intersection should not be equal to phi. Intersection should either be this. Intersection should either have a functional dependency on either one of them, right? Either on R1 or either on R2. Good. Let's move forward. Relation has the following functional dependencies: is decomposed, is decomposed. Let me remove this and put it here. Okay, so it is decomposed here into these three, right? So the decomposition is lossy because E comma S is E comma C is missing or not. So let me check. Okay, let me check. So firstly, check for B comma B arrow A. Let's not check for B arrow A. Let's just check whether the given one exists or not, right? E arrow C. Let's check for E arrow C. So uniting these three over here, something similar to, but EROC will directly exist in R2, right? While writing down all the possible uh, functional FDs, functional dependencies, CROC would exist. and the other one would be EROEC, right? And the other one would be EROEC. So finally, this is false. Let's go for other one. BROD, does it exist or not? So no, BROD would exist right here in R3 similar case. So even this is wrong. Uh, so let's check. Okay, it's R2 union R3. So is there a common element or is there a common attribute between them? No, there is no common attribute between them. So this is true, and hence third option would be correct. Let's move forward. In the given relation, the following functional dependencies, when they are decomposed, let's check. Okay, choose the correct. So over here, BROC would make the decomposition lossless. I don't think that would be case, because here let's see in R1. Okay, so B could reach E, right? B could reach E from R1, and from R2 E itself could reach C. Okay, that is a possibility. So this is wrong. This is wrong. Now BROD, does that is that possible? No, even that is wrong, because in the R3 we can directly reach D. CROE makes the decomposition lossless. CROE makes the, but it exists right here in R2, so even that is wrong. So the final thing that we can say, the given decomposition is lossless itself, right? Now let's check. Given relation is decomposed into the following relation. Okay, we decomposed it right here. Okay, let me add the arrow. I want to add the arrow. Okay. Uh, the decomposition is lossy. Okay, this is true if we find that R is a subset of naturally joining all of them, and it is lossless if no, it becomes lossy if it is equals to no, and it becomes lossless. Okay, so what we are for actually finding is the incorrect statement. So these statements are true, right? These statements are true and these statements are false. So in this case, B and C would be our answer, right? Let's again go to this. Lossless joint decomposition ensures dependency preservation. I guess so. Uh, a decomposition that preserves the dependencies ensure that its joint will be lossless as well. I think this statement is true by itself. However, I have some doubts in the first one. A lossless joint decomposition ensures dependency preservation. Lossless joint decomposition. I don't think that is the case, because let me check. So we would have to find this by trial and error. Okay. If both of them are correct, we are correct. If one of them is correct, this one is definitely wrong. This one is definitely wrong. Okay. In the relation R, we have functional dependencies. These are divided into the following sub-relations, R1, R2, and R3. The decomposition is lossless. Okay, so what we need to find is it lossless, is it this and that. So basically the keywords are dependency preserving and lossless. So for lossless, what we can check is R1 union R2 union R3. Do they equal to R? The second statement is R1 intersection R2 intersection R3. So these arrow would mean functional dependencies. Okay. So are they functional dependency of R1? Either R1, either R2, or either R3. Okay. These line means functional dependencies. Do remember that. Do remember that. And the final one is R1. They must have at least a common attribute between them. R2 intersection R3 should not be null, right? Should not be 5. These are the statements that we need to check. Let me put this in. Okay. And this one. So basically, a, does the union cover all the attributes in this? So R1 union R2 union R3. So A, B, C, and D. Okay. This one is true. A is the intersection having some common attribute between them. Okay, so these two individually have a common attribute B, and these two individually have a common attribute C. I don't know, does that count or not? Does that count? Because if that is so, see, individually between these two, it is true. But when it comes to these R1 and R3, this R1 and R3, then it would be incorrect. So I think the joint would be lossy. If I am correct, the joint would be lossy. If it is not lossy, I would be let me do this. Okay, let me put the decomposition as lossy. If I can make it lossy, then then this one is violated. Then this criteria is violated. We haven't even reached till here. Okay, this criteria is violated, and if it is not lossy, then this is not violated. Okay, we would have to check this through trial and error. Let's check for the functional dependencies. Okay, let's check for functional dependencies. Does A arrow B exist? So A arrow B would exist here in R1. Yes. Does B arrow C exist? Yes, it does exist in R2. Does C arrow D exist? Yes, it directly exists. So it is dependency preserving. It is dependency preserving. How many questions are there? Okay, good. A relation R A B C D with the following functional dependencies is decomposed here. Choose the correct. Okay, I am giving this to you to solve. Okay, you solve this. I have told you how you solve this. How many tuples will be generated after the natural join between the two relation in the figures? I would have to do this. So department is common between them. So obviously natural joint would be the Cartesian product between the common. So okay, first element, okay, one element. Then let's go to production, 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 meaning and production here. Okay, just talking about production. So two joints, meaning two more relations, two more tuples. Then finally accounts, right? Same is the case with accounts. Joining accounts twice. Okay, so the total of five elements. Okay, total of five tuples. For choose all the correct statement for the decomposition to be lossless. Okay, uh, R must always hold. A given relation R is decomposed into R1 and R2. A set of functional dependencies associated with R is empty. The minimum number of what? Okay, this is a big question. Then what is the minimum number of functional dependencies required to make the decomposition lossless? Okay, so making the decomposition lossless would mean to make the function dependency preserving. So if the set of functional dependencies associated with R is empty, okay, what are the minimum number of functional dependencies required to make the decomposition lossless? Okay, so it is quite easy, right? Usually they provide us with R and F. This time they are saying that F is a null set. What they are asking is how to make it lossless, how many elements to add in F to make the relation lossless or the decomposition lossless. So to do that you must be able to cover all of this. I think only one relation would be enough because they are asking minimum number would be one. Let's check. I think they hold a personal grudge against me. Let's check the answers. Yes, only one would be required. Okay, any one of you can make any one of them. So what they are saying that this may not always hold. Okay, so this one is actually true. The mistake that I made here corresponds and actually makes the answer that we wrote above right. Let me check where did I do it. Where did I do it? Here, right? It is lossless. It is lossless. Hence, that one may or this one may not always hold. Okay, this one identity may not always hold. That's something that we learned right now. What is wrong, what other things are wrong. Okay, this is something that I left to you. Okay, the correct statement is 0, so both the statements here are incorrect. Both the statements are incorrect. So function being lossless does not ensure dependency preservation, and decomposition that preserves dependency does not ensure that the join will be all lossless as well. Okay, adding B and D would make it lossless. Let's move forward. The second one, why is the second one incorrect? A relation ABCDE, for a relation ABCDE, the functional dependencies are and the following functional dependencies, it is decomposed right here. Choose the correct option. Okay. So since it is decomposed into three, and this relation may not always hold, right? As we have just learned that this relation may not always hold. Let's also check this here. All right, to make the decomposition lossless. Okay, so decomposition of R and at least one of the following. Okay, at least one of them. So this may be true, this may not be true, right? We only need one of them, either this or either that, but not both. but not both. So what the mistake that I did here was assume that this should be case always. However, you can just work with this much, okay? R1 union R2 not being phi, all right, or R2 union R3, or even R1 union R3, R1 intersection, okay, R1 intersection R3, R1 intersection R2, R2 intersection R3, okay. So that is something we learned, that only one of them must be true and not all. We only need one of them to make it lossless. Leaving a question to you people. I think we have completed all of it. So let me end this session right here, completing 5.5. All right. Goodbye, and let's meet again for activity.